Hi, it's time for another math easy solution. Time to discuss a problems plus example. Basically, problems plus is at the end of each chapter in my calculus book. It's some pretty interesting and advanced example that they have. And in this example, we're going to go over one that involves integral substitution and solve this example, which is pretty interesting. Basically, part A of it says prove that if f, the function f, is a continuous function, then the integral from 0 to a of f of x dx equals the integral from 0 to a of f of a minus x dx. And then part B says use part A to show that the integral from 0 to pi over 2 of sine power of n of x all divided by sine power of n plus cos power of n dx is equal to, forgot to add this here, equal to pi over 4 for all positive numbers n. Yeah, so now when we're looking at this part A right here, at first sight, like I wrote down here, the given equation may appear baffling. For example, you could ask yourself the question, how is it possible to connect the left side to the right side when it just clearly looks different, even though doesn't look that much different, but the fact that it's simple integral, but then all of a sudden there's a random a minus x there, it should be different. But one thing you should realize is oftentimes functions can be simply rearranged and written slightly differently, yet still being the same answer. And a great tool for doing just that is the substitution rule for integrals. So we can try that to see if we can rearrange the right side of the integral to match that of the left side. Yeah, so let's just write the right side down. So integral from 0 to a of f of a minus x dx. So if we want to make it look like this one, integral from 0 to a of f of x dx, what we could use is the substitution rule. So we go let u equals to a minus x. So when we have this, now du, in this case when you take the derivative, is equal to, well, just negative dx, and at x equals to 0, yeah, at x equals to 0, if we plug that in, u is just a minus 0 is just equal to a. Let's write a better equal sign. So at x equals to a, to get these two from the range of this integral from 0 to 1, or the interval. So now from a we have u is equal to a minus x is a, so is a minus a is 0. So putting this all together, what we have is the integral from 0 to a of f of a minus x dx is simply equal to, and now when we're changing the variables, so now u at x equals to 0, u equals a, so it's a, and then it's up to x equals to a, whereas u is equal to 0. So from a to 0 of f of u, so a minus x is equal to u. So all we're doing is changing this. Now the dx is equal to negative du. So this dx is negative du, so put a negative sign here. But as you can see here, the intervals from a to 0, and as you recall from my earlier videos on integration, you could just flip these around. So if you look at my earlier video about integral properties, you could flip these around and just add a negative sign. So this would just simply equal to 0 to a, and is positive now, of f of u du. Yeah, and basically this just proves that the left and right side are equal. This is the same thing, this is just different variable, same as writing basically integral from 0 to a of f of, let's say, x dx, or even if you would just change it up again, 0 to a of f of z dz. So it doesn't matter what you use, this is the same thing. So basically we've just proved that part. Yeah, so now let's go back to scroll back up and now look at part B, which says use part A to show that this integral is equal to pi over 4 for basically all positive values of n right here. Yeah, so now if we were to just write this down, so when we're going to apply it, and again, and when we apply it, we use part A, but where A is equal to pi over 2. So let's go all the way down here. So part B. So we're going to apply part A with A equals 2 pi over 2. So what we have now, and also I'm going to let I equals to this entire integral, so let integral from 0 to a, which is again pi over 2, of now sine nx over, and it's going to be sine nx power of n. Let's write this a bit neater. Then we have cos nx dx. This equals 2 integral from 0 to pi over 2. Now we could just simply apply the a minus x inside, because it'd be the exact same thing. So now we have a minus, well, where the a is pi over 2. Pi over 2 minus x all over sine n pi over 2 minus x, and then plus cosine n pi over 2 minus x, and then dx right there. And now what I'm also going to do is, as you can see, this is sine pi over 2 minus x, and this cosine pi over 2 minus x. If you recall my earlier videos on the identity, so recall the trig identities, write these down, identities, basically sine of pi over 2 minus x is simply equal to cosine of x. And also, and then the other way around is the same thing. So cosine pi over 2 minus x is equal to sine of x. And you can see that in my earlier video. And basically the sine and cosine graphs, they're just literally separated by pi over 2 distance. And you could learn more about that in my earlier video. Yeah, so now what we're going to do is basically apply this inside of this big integral right there. So what we have now is I is equal to integral from pi over 2, and then I'm gonna just put that in here. So now this cos of x becomes, this sine to the power of n of pi over 2 minus x, that just equals to cosine to the power of n of x. So it'd be cosine, and then this becomes sine. So that's the only difference. So now we have cosine of n of x, and then we have cosine nx plus sine power of n of x dx. And now what I'm going to do is basically note that the denominator right here, this cosine n of x plus sine power of n of x, is the same as this one right here. So if we equate them, so again, this is the same thing, this all equals, they're always the same here. 0 to pi over 2 of sine n of x. Let's write this down better. Sine n of x cosine x n plus sine n of x dx. So these are the same. So what, and the denominators are the same. I'll just write these down. So basically same denominator. So we could add up these two matching integrals. Denominator, so same denominator, so what we could do is write 2i, so multiplied by 2, because we're adding, is simply equal to 0 to pi, and since we're adding the same common denominator, this just equals to cosine n of x plus sine n of x, and then the common denominators are the same, n of x plus sine n of x. And again, you can add up integrals like this, and you can learn more about that in my earlier videos on integration. So now that we have this just simply cancels, and we're left with integral from 0 to pi over 2, and that's just 1. So notice it's the same top and bottom, they cancel. We want dx, and then this equals to the integral from, actually this is when you evaluated 1, that's just going to be x. And evaluate from 0 to pi over 2, which equals 2 pi over 2 minus 0, or pi over 2. Thus we have 2i is equal to pi over 2, or I is equal to pi over 4. And again, the n's cancel right here. And I want to make a note that in this case we have n is a positive integer. Yeah, n is greater than 0, because if n was negative, you would have something like a 1 over, actually you'll have a common denominator like this. Let's go sine, for example, let's say negative 2 of x, and then sine, this is the same thing as writing 1 over 2 of x. And then when this becomes 0, this goes to infinity. So again, this is plus 1 over cosine squared of x. And then as x goes to 0, this sine squared x goes to 0, and 1 over sine squared x goes to infinity. So you can't solve that properly for this one. You'll have an improper integral over there. And I'll just write that down. This is improper integral. So in this case, we're just dealing with when it's greater than 0. Yeah, and if basically if we have n equals to 0, then you get even even crazier results, and then you'll have like a 0 over 0, which equals, well, what is that? So you have a 0 over 0 possible. Yeah, and in fact, as I showed in my earlier video, basically this is undefined, but you could, but you can define it, but can define, this is pretty interesting, can define it as equaling to 1. Again, watch my earlier video, put in the video link below. So you could define it as equaling to 1, and in that case, if we have it equals to 1, then we have integral from 0 to pi over 2 of sine, so basically sine 0x equals to cos 0 of x equals to 1. So we'll have a 1 over 1 plus 1 dx equals to, well, 0 pi over 2, 1 over, and then this is a 2 dx. So this is not the same as, no, actually this is the same. Actually, my calculus book didn't cover this. And I'm doing this actually, I haven't done this before. Let's just do this live. So 0 to pi over 2, and when you evaluate this, this just becomes 1 over 2 dx right here. I mean, this is going to be x evaluated from 0 to pi over 2. So to take the 1 over 2 out equals 2 pi over 2 minus 0 equals pi over 4. So yeah, actually, yeah, it does work for even for 0. So I'll put that right there. That's pretty good. Got that on the fly. Yeah, now one more thing I want to just point out is basically if we graph the integrand, which is the function inside integral for different values of n, we see that it does seem plausible that they all have the same value. Yeah, so if we look at this function here, the blue is where n equals to 1. So sine x divided by sine x plus cos x. And the red is n equals to 2. We have here n equals to 3 is the orange, and then the green is n equals to 4. So roughly this is where it is at the pi over 2 is roughly equal to, yeah, roughly this is 1.57. So we're looking at integral underneath here. So if you look at this blue one right here, this has, it's smaller past this point than the other one, so it has a small area here, but then it has a bigger area across here. So it's bigger here, then goes smaller, and likewise with the red, it's smaller, so it's less here, but higher here. So it offsets the lower values below this value here, but with the greater values on the right side. And same with every single other one, as whichever one is the least, like the green is the least one, that's the x power 4. As you get past this point, it's the highest on this side. So it looks like it's symmetrical, and you'll eventually get the same exact value. So it doesn't matter what value of n, as long as it's not negative, because you might, yeah, you'll have an improper integral otherwise, because it goes to infinity there. Anyways, yeah, that is all for today. Hopefully you'll learn from this pretty interesting and extensive example, this advanced problems plus example. And also make sure to watch my earlier problems plus examples, which are pretty interesting and useful just for getting a better grasp on mathematics. Anyways, that's all for today. If you learned, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.